Good day, everybody. Today we are going to take a look at the second section of our unit on momentum, where we take a look at the conservation of momentum and collisions. So first of all, there we go. First of all, we're going to talk about the law of conservation of momentum. This law is as fundamental as the law of conservation of energy. It is just as important. However, it's a little bit more difficult to work with. The law of conservation of momentum states the total momentum of a system will remain constant in the absence of external forces. Now, what's confusing about this is that you have to define what your system is. Now, for us, our system is always going to be 2, maybe 3 objects large. Never going to be looking at anything bigger than that. But this can be increased up to the scale of the universe, where the total momentum of everything in the universe is actually 0. The total, the sum of all the momenta of every single object in the universe actually comes out to be 0, because the momentum has to be conserved. Now, we're going to be looking at a much smaller scale, 2 objects or so at a time. So we are going to see it as the momentum of the system at the beginning is equal to the momentum of the system at the end. And this is going to be the equation that we use. So here is the initial side. Here is the final side. Now, notice that it's still the equation of momentum, mass times velocity. 2 masses, m1 and m2, and 4 velocities, v1 initial and v1 final, v2 initial and v2 final. Conservation of momentum and the collisions are not difficult in terms of complicated math. The difficulty actually lies in simply keeping track of what you are working with. Now, in terms of the collisions, most collisions in real life are some combination of elastic and inelastic. But we're going to be taking a look at the ideal cases where the collision is either 100% elastic or 100% inelastic. What's the difference? In elastic collision, the 2 objects remain separate. Kinetic energy is conserved, and the equation for this is the same as the conservation of momentum equation. An inelastic collision, on the other hand, is when the 2 objects collide and then stick together. They join together into one singular mass. Now, in this case, some of that kinetic energy turns into heat. The equation is similar. Momentum is still conserved here, but because the 2 masses combine into a singular mass, they share one collective final velocity. So the first problem here is using conservation of momentum. A 25 kilogram rifle and a 0.01 kilogram bullet are at rest. Now, it doesn't say this, but think about how a rifle works. The bullet gets loaded into the rifle. When fired, the bullet travels 200 meters per second forward. Find the kickback velocity of the rifle. So m1 is going to be the rifle. And m1's initial velocity is going to be 0. m2 is the bullet. That's 0.01 kilograms. And that also starts at rest. Now, V2 final's velocity is 200 meters per second. and we're looking for V1 final. Going to our equation, just copying it down from where we had before. Since both objects initially start at rest, the entire left-hand side goes to 0. Now, we know M2 and we know V2 final. 0.01 times 200 will give us 2 kilogram meters per second for the final momentum of the bullet. So subtracting that from both sides, we'll get rid of it on the right, and it'll give us M1 V1 final equals negative 2 kilogram meters per second. Dividing both sides by M1, which is 2.5 kilograms, we get that the final velocity, let me rewrite that to make it a little neater, negative 0.8 meters per second. Think about this for a moment. Why is this velocity negative? Well, the total momentum of the system starts at 0, which means the total momentum of the system at the end also must be 0. But at the end, since one object moves forward, in order to cancel out that momentum, the other object has to move backwards. So this first problem here is going to be an elastic collision. A 1.2 kilogram cue ball rolls at 3.5 meters per second towards a stationary 8 ball, which is 1.6 kilograms. After they strike, the cue ball is now stationary. How fast is the 8 ball traveling? Start by logging our known information. Let's make M1 the cue ball. It has a mass of 1.2 kilograms. And it has a known starting velocity. We also know its final velocity. We know that it comes to rest. Now, mass 2 is the 8 ball. It's a little heavier, 1.6 kilograms, and it starts at rest. And so we're looking for V2 final. Because this is an elastic collision, the two objects remain separate. There should be an initial. Make sure you take your time when you're writing things out. As you can see, even I, with plenty of time and practice on these, can very easily make a mistake in writing these out just because there's a lot going on. So let's clean this equation up a little bit. M1 V1 final goes to 0 because V1 final is 0. And V2 initial is 0, so those go away as well. Which means that M1 V1 initial is equal to M2 V2 final. So to get V2 final by itself, we divide both sides by M2. Plug and chug, 1.2 kilograms times 3.5 meters per second divided by 1.6 kilograms. Go to your calculator and you can solve it out. Unit of kilograms will all cancel, and you should get about 2.6 meters per second. Now we have one final question here, and this is an inelastic collision. A 350 kilogram train car travels at 1.4 meters per second. It couples with a 400 kilogram train car traveling forward at 0.5 meters per second. What is the final velocity of the two-car train? Start with your givens. M1 is 350 kilograms, traveling at 1.4 meters per second. M2 is 400 kilograms, traveling at 0.5 meters per second. They're both positive velocities because both trains are moving in the forward direction. So they're going to combine together as the second car catches up to the first, or the first catches up to the second, I should say. Now, because the two train cars couple together, they combine as a singular mass. And so we're looking for that singular final velocity. So let's plug in what we know. 350 times 1.4 meters per second will give us 490 kilogram meters per second for the first momentum. Our second momentum, 400 times 0.5, is 200 kilogram meters per second. And that is equal to the sum of the two masses, which is 750 kilograms, times VF. Adding these two momentums together is 690 kilogram meters per second, equaling 750 kilograms. And we just divide both sides by the mass. .92 meters per second. And that's pretty much it.